Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you are able to join me today for this month's GPSX webinar. So this will be the last one of 2021, obviously, and we're looking forward to joining you next year and continuing on this series. I have with me today Nicholas Piccolo, my colleague, who's going to be talking about doing model calibration in GPSX. So the plan for today is, as it is usually, we're going to be doing some slideshows and talking and explaining much of our experience with calibrating these types of models. We're going to run some desktop simulations, as we always do. And what you can do is, if you have any questions that you would like us to address, please type them into the GoToWebinar questions box, which you'll find on your GoToWebinar dashboard. Type them in there. We'll just let those collect up. And then, as usual, at the end of the webinar, we will hang around for 5 or 10 minutes and answer as many of those as we can. So here is the plan for today. We're going to start with a bit of an explanation about calibration. What is calibration? Why is it important? And we'll move on to talking about how we go about calibrating a model. And that includes the step of analyzing your data. We'll talk about calibration methodology, so what things that you need to know, where you should be looking in your model to find the information that will help you set up a good calibration. And we'll talk about the order in which you do things and so on. And then we'll, during that period, also highlight a few features of the GPSX software that you would be able to use to kind of help the process along. So ways to get data in and out of GPSX, some methodologies to sort of handle all the information that you have and do some analysis and features to help you along the way. And as part of that, we will also be doing a desktop demonstration. We have put together a model and we have some real data, and we're going to calibrate that, at least a very short version of that. And as I mentioned earlier, if you have questions, please type them in the box and we will answer those when we get to the end of the presentation. Okay, so I'm going to hand it over to my colleague, Nick, now. He's going to introduce some of our slides here and kind of get things rolling. And then I'll come back a bit later on and talk about an example that we've put together. So over to you, Nick.
Okay, thank you, Spencer. So just before we get into how to calibrate, first I just wanted to get a little bit of a background on calibration in general and why we even need to calibrate our models. So basically, mathematical models are simplifications of complex systems. So they describe the key processes in the systems, but they don't reflect every single process in a system. So that's basically why we need to calibrate the models. Just as an example, in wastewater treatment systems, there's heterotrophic bacteria. And in reality, there's many, many different types of heterotrophic bacteria. We probably don't even know all the different types out there, but we typically just represent them as a few different biomass types in models. Thus, basically, calibration is just necessary due to our limited understanding of the real physical, chemical, and biological processes in the system, and also our desire to balance model simplicity with model accuracy, because we could easily just go ahead and add 10 different types of heterotrophs to our Mantis 2 model, for example, but I would argue that that wouldn't really make the model any more useful. It just make it a lot more confusing and more difficult to calibrate. All right, so what is calibration? Many people probably have a good idea of what calibration is, but just our definition is it's the process of adjusting model parameters to improve the fit between model and real data. So you can see here on the right, I just have this effluent total COD plot, pre-calibration, and then if I just click that animation, we can see it post-calibration. So I adjusted a few parameters, and now we can see that the model prediction is much more closely tracking the real data. The IWA actually released a good modeling practice guidelines for using activated sledge models in 2012, and they have a more formal definition of calibration as an iterative adjustment of the model parameters until simulation results match an observed set of data. So basically, calibration can focus on physical, operational, or biological parameters, and the choice of the parameters really just depends on the model, the purpose of the model, and the available data that you actually have for calibration. And some possible parameters that we calibrate in wastewater models are influent fractions, like the VSS to TSS ratio, the soluble to total COD ratio, or the COD to BOD ratio, settling parameters, so that could be the maximum settling velocity, the SVI, the hindered and flocculent settling parameters, and aeration parameters is just another example. So those would be like the alpha and beta factors or fouling factors on the diffusers, just things like that. All right. So I guess we just wanted to talk a little bit more about why calibration is important. And this slide kind of is showing just like the 3 stages of modeling. I say 3 stages very loosely because a modeling project is pretty non-linear. Sometimes you're jumping back in between these stages and you're just depending on your needs, you could go to validation, realize something's wrong, have to go back to calibration. But in general, these 3 steps are typically what you follow during a modeling project. And calibration is the first step and the most important step to using models effectively, because if your calibration is bad, your validation is going to tell you that, and then there's really no application for your model if it's not a very good model. So after calibration is the validation step, and that's kind of where you're just checking how good of a calibration you performed, typically using another data set from the same plant or same experiment that you calibrated your model on. And then after validation is the application step, where you're trying to get the model to tell you something that you don't know. So you're trying to use the validated model to predict what will happen in situations that have never been observed in this system before. So maybe if you're looking at a plant capacity increase study, you could use the model for that. Or maybe if you're looking to do some operational or control changes, or maybe looking at a cost reduction optimization, the possibilities are really endless once you have a well-calibrated and validated model. You can apply it to many different things. All right, so before we get into calibration, we first want to talk a bit about analyzing your data. And by the strictest definition, this data analysis step isn't actually a part of the calibration process. It's actually the step before calibration. However, if you have bad data, you're going to have a really bad time trying to calibrate your model. And in practice, we find that sometimes when you're having trouble with your calibration, it's because you need to go back to your data and check that you actually analyzed it and cleaned it up correctly. So for this reason, a pretty sizable portion of this webinar is going to be devoted to the pre-calibration data analysis, even though by the strictest definition, it's not technically calibration. So just an outline of what we're going to be talking about with respect to data analysis, data collection, then choosing data sets to work with. So if you want to do a seasonal summer calibration and a winter calibration, also just mentioning that you need to look out for times where there was plant upgrades or equipment shutdowns. Checking the data, so this is looking at the influent data, specifically looking at the characterization and comparing it to some typical influent ratios, and then also checking the mass balances, so that's just the mass balances around the clarifiers, and then finally getting your data into GPSX. So this is just a little additional resource also from that GMP report I mentioned earlier. So this is just a flowchart showing their data collection and reconciliation process from that report. It's just something if you want to look at more closely, you can go check out that report and kind of see how they have broken down the process into more finely detailed steps. All right, so first is data collection. So I'm just going to give a little bit of a breakdown of the most important data to collect at your facility. This certainly isn't going to be an exhaustive list of the data you can collect, and you can also certainly get by with less data than what I'm going to show you here, but ideally you want to be able to get your hands on most of this data. So for the influent, you want the flow data, the temperature data, the pH data, the COD, the BOD, TSS, VSS, TKN, ammonia, and any phosphorus data you can get. For the primary clarifier, the most important data is the TSS and the flow data in the effluent. And then for the bioreactors, at the very minimum, you want the MLSS, the MLVSS, and the DO data leaving the bioreactors. From the effluent, you want the flow, the COD, BOD, TSS, TKN, ammonia, total phosphorus, and then from all the different sludge streams, so the primary sludge and the WAS, RAS, and the effluent of the anaerobic digester, it'd be ideal if you could get flow data as well as solids data, so TSS and VSS. This is just another screen grab from the GMP report, just showing all the data they recommend you collect. It's pretty unlikely that you're ever going to be able to collect this much data, but if you do have the resources, why not? You can do it. I personally have never done a project where we've had access to even like a third of this data, and those projects still turned out great. So you certainly don't need all this data, but it is obviously very helpful to have as much data as you can, as long as the data is of high quality. All right, so next we're going to talk a bit about choosing an appropriate data set. And this step is pretty important because if you have careful thought at this stage, it's going to save you a lot of headaches down the line. So again, from this report, they have a quote in there that says, if the model is calibrated based on erroneous data, the predictive power of the model is compromised. Now, this is a fairly obvious quote. If your data isn't great and you try to get your model to match it, then you're probably wasting your efforts because there's no point having a model that is just matched to bad data. So it's really key to make sure that you are confident and comfortable with the data that you're actually using to calibrate. So I'm just going to go through some data sets to avoid. One thing to look out for is stuff directly, any data that you collect that's directly following plant upgrades or equipment shutdowns. So you really need to communicate with the operators and with your clients to make sure that you're not getting, or to make sure at least that you know what's going on at the plant when this data was collected. One of my colleagues was once trying to calibrate the MLSS in the bioreactors in a project he was working on, and he didn't know that at the plant they had actually taken a bioreactor offline. So he was seeing very high MLSS data from the client, and because he had an extra bioreactor than what they actually had, basically, and he wasn't able to get it to match because there's just more volume for the same amount of solids in the model than there was at the plant. So it was a battle he couldn't have won until he finally talked to the client. He was like, "Oh yeah, we took that bioreactor offline." So you always need to make sure that you're communicating and know exactly what's going on when your data was collected. Another thing to look out for is seasonal transition, especially if you don't have dynamic temperature data. So when the season is transitioning, say from summer to winter or winter to summer, the growth rates can change really rapidly. So if it's that time of year and you don't actually have the temperature data for every day or every any sort of dynamic profile of the temperature, then the models are not going to be able to capture the changes in the growth rates that are happening during that time. So it's best to just stick to a summer or stick to a winter unless you have the data that you can actually do a transition period like that. And then finally, just uncharacteristic performance in general. So if there's a wet weather event or some sort of shock loading event, you don't really want to calibrate your model to that. If you calibrate your model, for example, to a wet weather event, and then use the same model to predict day-to-day operation, it's obviously not going to be a great or very useful for predicting just a typical day's operation at the plant. All right, so the next thing we want to look at is the Influent. Getting your Influent data right is very important. So it's a good idea to go through and at least check these ratios. So these are the VSS to TSS ratio, the BOD to COD ratio, the ammonia to TKN ratio, and the soluble COD to total COD ratio. So you can see in the table here, I just list some of the values of the typical range of these ratios. And the values of these ratios are pretty consistent for municipal wastewaters. So if your influent concentrations are resulting in values of these ratios that are very consistently out of these bounds, or just jumping all around to each side of the bounds or something like that, then you either have a very unique wastewater, or more likely you should probably question your data and collect some more for validation purposes. Obviously, if you're dealing with an industrial wastewater or something very irregular like that, then you can expect maybe some of your values will be outside of these typical ranges. But for municipal wastewaters, you can be a pretty safe bet that it's going to fall within these ranges. So it's just a good thing to check. So I just now wanted to take a second to briefly show the Influent Advisor tool in GPSX and highlight that it kind of performs similar checks as those influent ratio checks. It doesn't flag the ratios per se, but in general, it doesn't allow you to enter any concentrations that are going to lead to unrealistic or physically impossible values of the state variables. So you can enter your influent there on the left, and then the state variables are calculated here on the right. And you can also see some of the ratios from the previous slide are actually in this bottom right corner here. So if I just bring that up, you can see the ammonia to TKN ratio is there, and the VSS to TSS ratio, and the BOD to COD. So those are all calculated for you there. So if you want to do a quick check after you enter your data into the Influent Advisor, you can just go look down there and see how your data is fitting into those ratios. All right, so another crucial step is checking your data using the mass balance. So if you analyze your data and the mass going into the secondary clarifiers does not equal the mass coming out, then the model MLSS is never going to match the data. And this is because the model follows the conservation of mass. So in the model, the mass is always going to be conserved. The mass balance is always going to close because the model is always obviously assuming the mass is balanced. So if the data doesn't have a mass balance in it, then you're not going to be able to get your data to match the model. So you can check the mass balance at steady state using the equations here on the slide to see if the mass flow of solids into the clarifier is roughly equal to the mass flow out of the clarifier. But there's also this option of calculating the cumulative mass balance, which I prefer because I think it gives you a lot more insight into your data. So to do this, you basically just follow these steps. First, calculate the solids in and solids out for every instance possible over the calibration period. So that's every time point that you have all these necessary pieces of data to calculate both the solids in and solids out value. Then you accumulate the solids in and solids out over the calibration period. So you're just doing a running total over the whole period. And then finally, you just plot the solids in versus solids out. So you plot those two accumulations versus each other. And basically, hopefully, if you mass actually balance, then you end up with a very nice line like this blue one here. That's showing the actual mass balance, and that red line is showing the perfect mass balance. So using this cumulative mass balance, you get a lot more precise information about the performance of the plant, and you can kind of notice where issues are arising. So if you notice that the actual mass balance line deviates from the perfect mass balance line, then you know something there is a bit weird with the data. Maybe there was a sensor issue, or you recorded some incorrect sludge hauling numbers or something like that. So this is just a good exercise and a good check to know if there's maybe some data that you shouldn't be using just because it's way off of the perfect mass balance line. All right, so once you're happy with your data, you actually now need to get it into GPSX so you can drive the model and perform the calibrations. So there's two reasons that we really want to get the data into GPSX, which are the reasons I just said. Basically, while it's important to still have to have good data for indicator variables, so the output data that you're actually calibrating to, like the concentrations and sludge production and stuff, you also want to have good data for the input. So like the operational settings, the DO set points, the pump flow rates, things like that. You also want to make sure that data is really good because that's actually going to be driving the GPSX model via the input controllers. Here I've just listed a few methods for getting data into GPSX. You can use a spreadsheet, enter columns of data into that spreadsheet, and then just link that spreadsheet to GPSX. You can copy and paste values into the data fields that are in GPSX, or you can even go into the input menus and manually enter the steady state values that way. If you want to learn more about data input and output in GPSX, you can check out tutorial 6 on the YouTube channel or in the tutorial guide. And there's also the GPSX user guide, which has a lot of information about a lot of things in GPSX and does have a sizable section on data input and output. Okay, so we've basically wrapped up the data talk, and now we're going to get into the actual model calibration methodology. So I'm just going to go and give a little bit of a general outline of what we're going to be talking about. So the general outline for model calibration is as follows. First, we choose and calculate an appropriate steady state data set. So that's a starting point for the dynamic simulation. Then we set up the layout with the correct physical and environmental specifications. Then we want to select an appropriate influent model. Then we're going to select our calibration targets. So that could be MLSS, sludge production, effluent concentrations. And then we actually do the meat of the calibration. So we run the simulations, we determine what parameters we need to adjust, we adjust those parameters, and then we repeat these steps until we're satisfied with the fit. And then lastly, we validate with a testing data set. It's not really technically a part of calibration, but it's kind of the next logical step is obviously you want to validate your calibration with some other data. All right, so I'm just going to go through these steps in a little bit more detail. So first is calculating the right steady state and dynamic data sets. So the steady state data set is very important because it serves as the initial condition for the dynamic simulation. So it is a good idea if you can get it to accurately represent the status of the plant right before the dynamic simulation starts. So if possible, you want to use data prior to your dynamic data to create your steady state data set. A lot of people just take an average of a year's worth of dynamic data, or just average their dynamic data that they're going to be using to dynamically drive the model and use that as the steady state set. But it doesn't actually really make a lot of sense. It makes more sense to maybe step back 5-10 days, take an average of that data, because that gives more of an idea of what the status of the plant was right before the dynamic simulation started. And with the dynamic data, you typically want to choose a period representative of typical plant operation. So basically just looking at that data analysis stuff we just talked about, you want to choose a time period that has a reasonably matching mass balance and good influent ratios and things of that nature. The next step is setting up the layout with the correct physical and environmental specs. So this is fairly self-explanatory. You just want to make sure all the tank volumes are correct, all the tank depths are correct. It's very important to go to the clarifiers, make sure the surface areas there are correct, and the clarifier depths. Also, if your plant is very far from sea level, you might want to go and change the elevation. You can get that in the simulation menu in GPSX as well. Next, you want to select an appropriate influent model. So in general, we recommend that if you have COD data, you should always use a COD-driven influent model. So that's the COD states influent model or the COD-based influent model. And that's just because COD is a more reliable measurement than BOD. And models are typically based, or our model is based on the COD balance, where COD is conserved. So it's nice to have that, the influent of the model being COD, so that it kind of just closes it nicely throughout the whole simulation. If you don't have COD data though, or you're not very confident in your COD data, then choose a model based on the data you are most confident in. One project I worked on, I actually ended up using the TSS FRAC influent model because they had very frequent TSS data that they had a high confidence in, and they had infrequent BOD data and almost no COD data. And that project went really well. I didn't have any problems with using it. So it's not that you can't use the other models. It's just if you do have good COD data, it's usually the best choice. All right, so moving on to the selection of calibration targets. Typically, you want to choose key performance markers. And what I mean by this is basically if you're calibrating a model that's going to be used to investigate if your facility will be able to meet nitrogen effluent limits, for example, then you want to make sure your total nitrogen and ammonia and nitrate and just all the nitrogen variables are used as the calibration targets. You want to think about what the application of the model is and make sure that when you're calibrating it, you get those things as well calibrated as possible. Some other common targets, though, that you always basically want to be considering when you're calibrating the model is the MLSS concentration, the sludge production, the DO concentrations, the effluent concentrations, and the operating cost if you are trying to do some sort of cost model. And then just some more facility-dependent ones. There could be biofilm thickness if you're doing an attached growth system. If you have any resource recovery, maybe you want to calibrate your struvite recovery numbers. And then obviously, if you have an anaerobic digester, you're probably interested in calibrating your VSS destruction and your gas production in the anaerobic digester. All right, so now we're going to discuss a bit about what parameters to actually adjust. So in many cases, a good calibration can actually just be achieved by adjusting the influent characterization and the settling parameters. We're going to get into more specifics on what parameters within these two categories specifically you should be adjusting in the upcoming slides, but I'm just going to talk about a few more parameters that you sometimes need to adjust before that. So the biological models typically are pretty well calibrated, and they don't usually need major adjustment. But sometimes if you do notice that for whatever reason, some of the concentrations in the effluent are off or something like that, and you do need to get into calibrating the biological models, you should stick to the growth rates and the half saturation rates because they can actually be more variable from plant to plant. But I would advise against changing the yields or inert fractions or basically any of those stoichiometric factors because those are very well known and they typically wouldn't change in reality, so you shouldn't be changing them in the model. Some other parameters that may play a role in some systems are aeration parameters like the oxygen transfer efficiency, alpha factor, fouling factors, solids handling performance, so that could be dewatering efficiency, the tertiary treatment, so if you have any filtration or chlorination, you're going to need to calibrate that. and then biofilm parameters if you have a biofilm system, so the surface area of the support material or the maximum thickness of the biofilm. Those could be things that you need to calibrate as well. Okay, so as I said, I'm going to quickly touch now on the two more key areas of calibration. So that's the influent characterization and the settling parameters. I'm going to start here with the influent characterization. So the influent concentrations are obviously very important, as changing the influent is basically the one thing that you can be sure is going to affect everything else in the model. So a very important thing is correct partitioning of the COD into the soluble substrate, the particulate substrate, and the particulate inerts. Because this affects the DO in the mixed liquor volatile suspended solids, as well as the soluble substrate is very important for any sort of nutrient removal. So if you're doing denitrification or biological phosphorus removal, it's really important that you get your soluble substrate number correct, because that has a very strong impact on the extent of those processes. So you use the influent advisor to control the distribution of the COD, the nitrogen, and the phosphorus into the biodegradable and inert fractions. And typically you're adjusting the influent ratio, so that's the VSS to TSS ratio, as well as the nitrogen and phosphorus fractions, and the stoichiometric ratio, so that's the soluble and inert fractions of the COD. One important parameter I just want to highlight is the particulate inert fraction of total COD. Basically, if we raise this fraction, then the MLSS in the bioreactors is going to increase. So this is a very handy parameter to use if you are trying to calibrate the MLSS. All right, now moving on to the settling parameters. A pretty useful feature of our clarifier models is the SVI correlation to settling parameters that we have. So if you have SVI data, you can feed it into the model and then calibrate the SVI correlation using the clarification parameter. If you don't have SVI or you don't want to use the correlation, you don't have to worry. You can still adjust the hindered and flocculent zone settling parameters to get your clarification calibrated. But a big thing with clarifiers is the physical setup. So I would say before changing anything, it's always worth it to go back, double check your physical setup if you're having any clarification issues. The feed point from bottom is particularly important. You don't want that to be anywhere near the top of the clarifier. And as well, it's worth to just go and check the surface area and the depth of the clarifier, again, before actually going and messing with any of the clarification parameters, because oftentimes that can be the issue. Something there has just been set up incorrectly. All right, so now that we actually know the common things to calibrate, we're going to talk a bit about how we actually do it. So obviously the very first step is just to run the simulation initially and identify what exactly is uncalibrated. And then you calibrate. We recommend in this order I'm about to show. It's just a general rule of thumb. Obviously, calibration is iterative, so this order may change. But generally, we say start with the influent, then calibrate the MLSS concentration, then calibrate the DO concentrations, then calibrate the sludge production, then the effluent concentrations, and then finally the operating costs, airflows, and pumping costs. So as I said, this is just one approach. It obviously is going to change a lot from case to case, but the one thing that we're never going to change is influent first. We always want to get our influent calibrated well so that we don't have any issues down the line where we need to change the influent and then the entire calibration gets screwed up. So other things can be different though. So depending on your type of facility, maybe you notice off the bat that your MLSS concentration is okay and you don't need to change anything initially. But later, maybe you're calibrating the effluent concentrations and you circle back to check on the MLSS and now it's off by a bit. So you have to go back and change some parameters and try to get that back matching again. So what I'm trying to say is basically there's no one single perfect method for calibration, and you're never going to find a flowchart that tells you exactly how to do it perfectly every time. But having a structure like this is helpful, especially to start, because you kind of have an idea of how to walk through it the first time, and then you can just go back and make your changes as you need to. So I just wanted to also share some things to keep in mind while you're calibrating your models. The first one is that you should have some strong evidence to support any parameter changes from default or measured values. So an example of strong evidence would be that you have a large contribution from an industrial wastewater. So in GPSX, the default parameters we have are for municipal wastewaters. So if you have an industrial wastewater, then it's not that hard to justify, oh, I need to change this parameter a little bit just to get this to match, and you can feel justified in that, knowing that these parameters were actually set up for a slightly different type of wastewater. But if you are calibrating a typical municipal plant and you find yourself changing, for example, lots of kinetics of multiple biomass, I would say it's probably a better idea to revisit your data analysis and to keep changing those kinetics, because it's likely that the problem is somewhere in the data and not with the actual kinetic parameters. Another thing to keep in mind is that the parameter influence on the simulation results should be significant to justify modifying the default values. So don't just drastically modify a well-defined parameter to marginally improve a poor fit. And also keep the variability of the data in mind. So obviously the data isn't perfect. There's inherent like standard deviations and stuff in all the data. So you don't need to chase precision that's not there. You don't need to try to get your line to cross every single point. You just want to get it within the right magnitude and just the right area and the right kind of trend. And that's typically good enough for calibration. Another thing is only change one thing at a time. Calibration is an iterative process, and many parameter changes can offset each other. So even if you're in a rush, I promise you it's going to save you a lot of time if you just stick to the strategy of only changing one parameter at a time. Because if you start changing multiple parameters, you're not going to know what parameter actually made the change that you're seeing, and it's just going to get very confusing. Finally, just a more general comment about critically apply engineering intuition when modifying parameters. So if you have an idea of the underlying model structure, that's always good to keep in mind, so you can kind of expect what your parameter changes are actually going to do to the model before you actually run it. It's just a good check in your head. And then also, you want to ensure that the adjusted values of the parameters are still in a realistic range even after they've been adjusted. So Appendix F of the Good Modeling Practice report that I was talking about earlier provides a parameter range reference for common parameters, so you can look at that and make sure that none of your parameters are outside of the range, of the typical range. All right, so finally, what I just wanted to talk about was some calibration features in GPSX. So GPSX comes with many built-in features, and a lot of these features you can actually leverage while you're calibrating your models. I'm just going to talk about a few of them here: scenarios, statistical features, and the optimizer or dynamic parameter estimation feature. All right, so scenarios are incredibly useful for model calibration. You can create as many scenarios as you'd like in GPSX, and in each scenario, you can specify changes to the model parameters that kind of define that specific scenario. So all the scenarios you create are saved in the scenario manager, so you can access the scenario manager by just clicking down here on the screen and then going to select scenario, and you can see all the different scenarios you have in your layout. Another good feature of this is that if you switch to a scenario, so in this case I switched to summer calibration, and then I go and click show here, I can see the scenario show window come up that displays the changes between that specific scenario and the base model. So you can see that here in the Influent, I made a couple changes to the VSS to TSS ratio and the particulate inert fraction. So you can see that I was doing some calibration here, and then a big thing is since this is the summer calibration, you can see that I changed the temperature from 20 to 28 to reflect the warmer temperature in the summer. So yeah, scenarios are just a really great way to kind of keep track of your calibration and of multiple calibrations if you're trying a couple different strategies. You can go to tutorial 3 on the YouTube channel or in the tutorial guide if you want to learn more about using scenarios. Another good feature is the statistics feature. It contains many useful options that can be used to get deeper insight into your calibration. So basically, all you have to do is right-click on any graph that contains external data and just click statistics, and that'll bring up the statistics tool, which just contains a bunch of options for different statistical reports. Here I've created a plot of simulated versus measured data with a 45-degree line superimposed onto it. So if the model was fitting the data perfectly, all of these dots here would be on this line. It's just really a nice way of visualizing your calibration progress and lets you see quickly if, for example, if you're mostly over predicting or under predicting, or if there's some sort of trend in the residuals, you can really quickly see that by looking at this plot. Finally, I wanted to talk about the optimizer or dynamic parameter estimator. It can essentially calibrate for you, but as a warning, you should always check the results versus your engineering intuition. For those who don't know what DPE is, basically it's a dynamic optimizer that allows you to set a time window for how frequently the manipulated variable is going to be changed. So in this case that I'm going to show here, I'm going to show an example of using the DPE to estimate the alpha value for aeration. So I'm trying to fit the model predicted airflow to some data that we have by adjusting the alpha value. So it's going to choose a new alpha value every 4 hours over the course of a 4-day simulation. So here we just see the default alpha value being used, and the airflow you can see is kind of on the high end. It's hitting the peaks okay, but it's definitely missing the valleys. So obviously using the default alpha value isn't the best option for this calibration. Then this is just showing using a calibrated alpha value. So this isn't using the dynamic parameter estimator. This is actually just kind of taking a look at the data and just manually adjusting the alpha value and seeing how well I can match to this airflow. So you can see that both the peaks and the valleys now are not being hit that well, and it's kind of like in the middle, just an average of the airflow data is what's being shown by the model predictions. And then finally, using the DPE with a 4-hour time window, I was able to calibrate the alpha value. So you can see here, this is the alpha value predictions that the DPA came up with. So there's kind of a diurnal profile here in the alpha value. And you can see now that the model is matching very well. The peaks and the valleys are both being matched very well because of the fact that the alpha value is now able to change dynamically over the course of the day. All right, so that's all I have in the slides for you, and I'm gonna throw it back to Spencer to just go over a bit of a desktop demonstration.
Thank you, Nick. I see that we have some questions now being entered into the questions box. So if you have a question that comes to mind, please feel free to enter that in. Oh, realize I'm not starting at the beginning here. I got to get my way to the correct slideshow here. Okay, we're going to jump straight to the GPSX layout. So, okay, so it wouldn't be a good traditional GPSX webinar if we didn't at least have some live desktop simulations happening. So what I've done is Nick and I put together this layout. It is kind of adapted a little bit from another layout, and we've got some data that we have put in there that is there to help us sort of illustrate the process of doing a calibration. So just real quick on here, this is just conventional activated sludge. We have an influent coming in. We have a primary clarifier, a plug flow reactor here, secondary clarifier, and then on to disinfection and the effluent. And then both the primary and secondary sludge is going to be going to this digester, onto dewatering, and the centrate is brought back around again. So anyway, it's pretty much a simple, straightforward activated sludge process. So I'm going to run, just to start things off here, a 10-day simulation. And it's going to be a dynamic simulation, but as you can see down here, we're doing a steady state solution first. So that means that we're starting the model as if this plant had undergone, normal kinds of loading for a period of time before we start this dynamic run here. So when Nick was mentioning earlier that it's important to make sure that you select a good period of time to get your data from, that is the reason here is because we want to make sure that we're starting from a reasonable point at the beginning of our dynamic simulation. So. Okay, so I'm reading in some dynamic data here. The influent flow is changing, temperature is changing, and so on. We're holding these average influent concentrations constant, but as you can see on the graph here, we've applied a daily diurnal pattern to them. So, and that gives us a little bit of interesting dynamics to look at. So, okay, so there's 10 days of simulation. This is all the influent information that we're reading in and that we're using. And we can see a few data points here that we've got as part of this simulation. And we can see that our TSS in the influent is not actually matching the data all that well. TSS is not a direct input in this influent model. We start with COD and some other things. So that's one thing that needs a little bit of attention and calibration. So let's look at the bioreactors themselves, those long plug flow system. We've got an MLSS number here that's the sort of the main lines going through the middle of that. We've got an airflow that goes up and down, and we've got some DO set points down here that are being read in. So we're going to come back and look at those again, and then here's our effluent numbers, and we can see places where we have some data points to match along with what the model's predicting. And as you can see here, it's not very good at the moment. The model's not well calibrated right out of the box. We can see here, for example, these black points along the bottom here are our effluent TSS numbers, and here's the model up here swinging back and forth. And in fact, our total COD here in the blue dots, we can't even see the total COD. It's actually off the top of the graph. So what that's telling us is the model's not very well calibrated, and we need to take a few steps to be able to deal with that. So what Nick wanted to show earlier was that there's usually, you start with your influent, right? We start with understanding that we have done a good calibration, or sorry, that we've done a good characterization of our influent information as part of the calibration of the model. So I'm going to actually create a new scenario here. So Nick mentioned earlier that this is often a good place to sort of create a brand new scenario. I'm going to call it calibration. And then now any changes that I make to the model will be given or collected up and stored under the name of that calibration scenario. And at any point, I can go back to the base model or any other type of calibration that I wanted to do. So in this particular case, this number over here was showing us that our TSS number is, the simulated TSS that we're using is too high. So that means that probably some of the stoichiometric ratios in our influent are probably not correct. We're reading in some real data, but we've left a lot of the other things at the default. So let's take a look at that. If I go in here, go to the Influent characterization menu, and as Nick mentioned earlier, we have this tool that's there to help you debug your data and to help it with your calibration. So if I look in the right-hand column here, we can see the TSS is about 350. And so for that given COD and other data points that we've entered here, that number is probably a little bit too big. So you can see the numbers that we have changed away from the defaults here as the blue ones. And so we've left all of these important ratios here, the VSS to TSS ratio, and then the breakdown of the COD into the different levels of biodegradability and solubility here. These are all left at the default value. So these are the kinds of things that, typically you're going to have measurements for these numbers, but this is the stuff that you're going to adjust in as part of your calibration. So I want to bring this number down. So what I'm going to do is I'm going to change the VSS to TSS ratio. That's going to, if I put this number up, that is going to bring the other number down. So if I make that 0.85 instead of 0.75, you'll notice immediately this number here dropped from 350 down to 311. So that's going to, I think, put us in the more correct position. And if I rerun our simulation here, we should find that our new influent characterization, our new influent numbers that we're seeing here are going to match to that data a little better. Now, in a real calibration of the model, you'll probably go through that with the nitrogen and the phosphorus as well, just to make sure that some of those ratios that you're using, that they match right on to the data that you have. If you have data for your influent and it's not an input into the model, then you got to make sure that your other things that are being calculated for you do match to the data that you have. Okay, so that's kind of got this. Now we seem like we're sort of hitting on those data points. You can try to keep in mind here that there was only one data point per day. This is a 10-day simulation. There was 10 individual data points. This is not uncommon, of course. Probably what these are a grab sample, a composite sample, a 24-hour composite sample of the data that was coming in. It's possible it was a grab sample too. Maybe they do that once a day. But the point being that this is not, you don't necessarily need your model to pass directly through each data point, because that data point does have some plus or minus, some uncertainty associated with it. We're just trying to get it to match up reasonably well in the right kind of neighborhood there. Okay, so now let's look at the rest of the model and see where we're at here. So in the bioreactors, the two things that we were looking at was the mixed liquor, which is here, and we can see that that number is still actually pretty good. Normally, the mixed liquor is something that you would be the next step in your process. After you characterize your influent, then you check to see whether your mixed liquor is okay. So it's a little bit low here. And by the way, I will talk about this thing here. This is kind of a, you know, a little bit of thing that we put in the data here to show something that we occasionally see in reality. And I'm sure for those of you who have done modeling long enough, you've seen other instances where you have some sort of like weird thing happening here. This is a case where you would have to say to yourself, with some of your own engineering judgment and experience, do I need to make the model match to this? Now, this one's a pretty extreme example. But the answer to this is I'm not going to do that. I'm going to ignore this little excursion here because it doesn't actually make any real engineering wastewater sense. This is obviously something to do with the measurement. It was, you know, something to do with the sensor. Well, I know personally that my mixed liquor would never increase by 100% and then back down again within like half a day. That's obviously just something that was going on with the sensor, so I'm not going to worry about it. We'll just ignore that. You could even potentially take those data points out of your calibration, or maybe use a week earlier or a week later, something. But Nick and I decided to leave this in here because it's representative of like the messiness of data that you get in reality. Okay, so back to the point was that our mixed liquor number, we actually don't need to adjust anything. It actually looks pretty good, so we're happy with that. Let's look at the airflow while we're here. Yeah, that's a little bit too high. Let's look at the effluent numbers. Well, they're much better now. I'm going to blow this up here. So if we look at our effluent solids numbers that were previously swinging back and forth like 20 or 30 milligrams per liter, we can now see that we've kind of got it into a more normal range because we now have a more appropriate amount of solids in our influent. But we're still not hitting these data points down here. And we can see that this effluent total BOD number in red is of course not right. And our COD, well, at least we can see it now on the graph, is also not correct. So we still have too many solids in the effluent. So that's probably the next place. So start with your influent, look at your mixed liquor, and now let's look at our effluent and see what we can do. I think in this case, because it's pretty much straight up solids, that is the problem. If I remember correctly, yeah, you can see here that our effluent soluble phosphorus is okay. It's the particulate phosphorus that's the problem. Okay, so we got too many solids here. So what we can do is actually adjust the calibration of the settling in the secondary clarifier. And as Nick mentioned, one of the very useful things that you can do is turn on this correlation so that you're using SVI and this clarification parameter. These two parameters I find are reasonably straightforward and intuitive to use, a little bit more so than the theoretical hindered and flocculant zone settling parameters. So let's work with these. I try to do that most of the time. And we can see here for this clarification parameter, that's what's going to control these concentrations, at least to a certain degree, in the effluent. What we're trying to do is calibrate the settling of the low concentrations in the top half of the clarifier. And we want to basically adjust those things. So it's between 0 and 1, and I'm going to increase it to 0.75 because what I want to do is make this stuff settle better. I want it to match more closely to what's really going on in that clarifier. So I forgot to mention it earlier. By the way, you'll notice that when you're in a scenario and you make a change to a parameter, it puts it in green, indicating that this is a scenario-specific value here. Okay, so let's run that again. So now we've made an adjustment to the settling parameter, and that is going to help us understand and see whether that makes an improvement. It makes quite a bit of an improvement here. And of course, now we're seeing pretty close to the correct values of all of this. So the model is now doing a much better job of keeping the solids in the clarifier and not letting them out over the overflow. And so our effluent numbers have now been kind of calibrated into the right place. So now, you don't typically just stop here. One of the important things is to go back and double check the other things in the model. So as Nick mentioned, it's important to not change several things at a time. You change them one at a time, but that also means, excuse me, that you need to go back and iterate through a couple times to make sure nothing else has been pushed off. So what I can see here is that looks pretty good. I'm going to go back and look at my influent number. Well, nothing changed here. That's just an influent calculation. But the bioreactor, okay, so now this is a much higher than it was before. It's gone up by maybe a few hundred milligrams per liter. So that means this probably needs some adjustment. So, and the reason for this, it makes sense. We've now kept more solids into our clarifier, so we're probably recycling more solids back into the bioreactor through the RAS. So this means that we now need to make an adjustment to bring this number back down to where it should be. And so that's an important thing to do. You always want to have your mixed liquor numbers correct. And in most cases, small adjustments to the mixed liquor like this can be handled and are due to not having the right amount of inert material in your influent. So if I go back and I take a look at the influent characterization, like I did before, so that this is the number I changed last time so that I have the right TSS. I didn't make any adjustments to these fractions here. So these are the fractions of total COD that get designated off to soluble inert, readily biodegradable substrate, particulate inerts, colloids, and then the last, anything that's left over goes into particulate, slowly biodegradable substrate. So basically, you set up where all of this goes. So 5% of it is inert, soluble inert, 20% of it is substrate, 13% of it is particulate inerts, and so on. And so you can juggle all this, and the remaining part of the 100% goes into the XS state variable, slowly biodegradable substrate. Okay, this is the one that's the important one here. Particulate inert fraction of total COD. This is the stuff that is the XI state variable, particulate inert organic COD. It is the stuff that is not going to be broken down by the biomass. It is just going to float in there and then float out, and it's going to settle out in the secondary clarifier and be recycled back, and it becomes a significant portion of your mixed liquor. For that reason, I can adjust the mixed liquor concentration by making a change to this variable. And in fact, matching it is the thing that you want to do. That is what's going to calibrate the model and get it into the right place. So I'm going to say, let's take half of this particulate inert material and then put it into the slowly biodegradable substrate. So I'm just going to cut this number in half. That may seem like a very large change, actually, by reducing that by half. But if you think about it, it's really just saying, of the 100% of all of the total COD, I'm just going to move like 6% of it from one place to the other. So we're going to basically keep it as a solid. It's a particulate, but we're going to move it from being non-biodegradable to biodegradable. Okay, so let's do that and then run that again. So yeah, it's very, very common to make adjustments to the particulate inert fraction during an influent characterization where you're trying to match your mixed liquor numbers. It's really an important key parameter in matching mixed liquor. And if you match your mixed liquor, then pretty much you'll match your sludge production as well, for the most part. Okay, so it's a little hard to see here, but basically we're matching this number right through here pretty well. There it's coming out on that side. So so let's call that well done. I think we've now corrected, now that we got the correct solids in the effluent, and all those solids are coming back into the bioreactor. We've now got the correct composition of the solids in terms of their biodegradability, and that all looks pretty good. Okay, now the last thing that I was interested in talking about was our aeration here. So one of the things that was being done here is we were reading in some DO numbers, and we were basically matching the DO numbers by having on a DO controller. This was also suggested as one of the sort of steps to doing setting up your calibration. Is it's often very handy to turn on a DO controller and read in a bunch of DO set points, and then that way you know that you're getting the correct amount of oxygen transfer while you're taking care of your biological part of your model. Later on, you can then actually just match up the airflow by adjusting some of the parameters like alpha. And then once you have that in place, then you can flip it back and forth either way, and it'll work. You can either read in the airflows or you can read in the DO set points, whatever you like. So what this means is we want to calibrate this airflow. I want to get the right amount of air being used to get the correct amount of oxygen transfer. So the biology we know is correct. It's got the right residual DO. It's got the right amount of biological activity. Everything's nitrifying the way that it should be. But we're showing here that the model thinks it needs a lot more air than it actually does. So we want to bring this number down and match these points. And you can do that actually by changing alpha. Now we have a lot of different settings for default alpha values based on what kind of technology you're using and so on. Right now we got, for this particular layout, this average alpha value that we're using throughout the length of the tank, and it's set to 0.6. So what this means is we're reducing by 40% the oxygen transfer based on this value. So alpha is kind of a fudge factor that you can use for calibration purposes. So if I want to bring this number down, that means I want to have more efficient oxygen transfer. So I should push this thing up. So we're going to move that up to 0.7 and we're going to rerun it again. Now that tells us it's more efficient. I don't need as much air to be able to match my DO. So it's showing here now it's using less air in order to hit the DO set points. And it's kind of matching a lot better, I would say. It's not spectacularly perfect. In fact, it looks like it's still overestimating a bit. So I tell you what, I'm going to stop this. Let's go back and make that 0.75, and we will run that again. Okay, that's much better. Okay, so now we feel like we're kind of passing through the midpoint of most of that data. And what that is telling us is that we now have sort of calibrated the oxygen transfer of this model. We are meeting the residual DO set points, and we're actually using the correct amount of air to make that happen. So I would say this is a pretty good fit. I'm just going to go back and double check, make sure our effluent numbers look okay. And let's reduce this down. Our DO should be, and our mixed liquor should be the same. And this, of course, is the same. That's an influent setting. So I think we can say this all looks pretty good. I think we'll call it done for this very, very simple example. Other things that you might want to have done and moved on, if you had the data, of course, is you could calibrate potentially other things. We could have gone to the details of seeing, for example, the digester gas production and see whether if we had gas production data, we could, potentially adjust some of the things there. In this particular case, we didn't have to adjust any of the biological parameters, but if you did have something weird going on at this plant where the biological activity was a little bit diminished because of something in the influent, you could have changed those things too. But actually, our numbers match pretty nicely here in this particular system. Okay, so I'm going to call that done, and I'm just going to pop back to our slides and kind of wind things up here. With a few final thoughts. We wanted to sort of provide a few last-minute guidelines. We always suggest selecting what we call typical plant performance. If I'm doing a calibration of a model of a facility and I'm doing it for the first time, it's best to try and ask, the operators of that facility, can you give me a period of data when the plant was running like it normally does, and use that. If you're going to start a dynamic simulation, like I was just doing there, you need to set up what the values will be used for at steady state prior to the beginning of the dynamic run. And it's good to actually grab some data that comes from the period before the dynamic run. Say, take the averages of, say, a month prior to the beginning of your dynamic run before you run 3 months of dynamic data. That way it will match the good starting point. Be aware and be willing to change some of the physical parameters that you're putting into your model in order to get the calibration done. Some physical data may not be exactly what they think they are. I've had lots of cases where people said, oh, yeah, there's a split there between the two lanes. It's a 50-50 split of flow. But the model's saying, no, it isn't. You probably have something other than a 50-50 split. Here's another example that I've also had several times of a digester volume. And in fact, it happens so often, we put in a new parameter here called effective volume fraction. This is showing 100%, but you might actually want to reduce it down, say, to 80% if you're not able to match your gas production, because you might have a not completely mixed digester, or you might have some of the digester volume taken up by struvite precipitation or something like that. So often, if somebody gives you a tank volume and you put that in the model and it's over predicting performance, it might tell you that you need to back it off a little bit to deal with some imperfect mixing or short circuiting of the flow as it goes through and out the other side. Always question your data. If you find, as Nick mentioned before, you have to change a lot of things, then you may need to go back and review the data that you're using and be willing to adjust and or throw out some of the data if it just doesn't work. The models are 100% based on mass balance, so they have to fit. But your data might, you might have one number that's not great for some reason with the sensor. There's no point in trying to force the model to match it because it won't happen. So experience has always shown us and everybody in this industry that the influent characterization is pretty much the most important part. It drives the whole rest of the model. So try to get that in line as best you can first. and be willing to iterate through a few times just to see if that latest change that you made causes anything else to kind of go out. You know, activated sludge has a big recycle in it, so sometimes changing things in the secondary clarifier will adjust things as it happens at the beginning. Or even if you're changing your calibration of your digester or your centrifuge, it might, you know, some centrate going back might change things a little bit too. So there's a couple of references here that we talked about today. IWA and publishing has put out these two reports here on influent characterization and on the guidelines for using activated sludge models. Those are both really great reports and might be very useful to you.